All right, class, welcome. Today, we're going to tackle a really fundamental component in power electronics. I'm talking about something that's working silently inside almost every single device you own, the diode rectifier. This is where the magic really begins, turning the power from the wall into power our gadgets can actually use.
So, here's the game plan for today. We're going to start with the why. What's the basic challenge we're trying to solve? Then we'll get into how well we're doing it, basically how we grade performance. After that, it's time for the what, the actual circuits themselves. And we'll wrap up with the which one, how you actually choose the right tool for the job. Okay, so let's just dive right in. We plug stuff into the wall and it just works, right? But here's the thing. The electricity coming out of that outlet is AC, alternating current. But all our cool electronics, our phones, our computers, they need DC, direct current. So that begs the question, why is this conversion from AC to DC so absolutely critical in the first place?
And this little block diagram really shows the heart of the whole operation. Everything from the charger for your phone to these massive industrial power supplies, they all rely on this one basic principle. You've got to take that wavy, oscillating AC from the source and turn it into the steady, flat DC that our electronic circuits need to actually function.
So a good way to think about it is this. A rectifier's main job, its core purpose, is to be a one-way street for electric current. It takes that back and forth AC signal and just forces it to flow in only one direction. That's what we mean by unidirectional.
Now, this is where we run into our first big engineering problem. The dream, the ideal goal, is that perfectly flat, smooth DC line. But in the real world, what we actually get from a simple rectifier looks more like this. It's got these bumps, these variations. We call that ripple. And honestly, taming that ripple, that's a huge part of power supply design.
Okay, so let's move on. How do we actually measure the quality of a rectifier's output? We need to put some numbers on this, right? It's that old engineering saying, if you can't measure it, you can't improve it. So how exactly do we know if a rectifier is any good? How do we give it a grade? Is it an A+ student, or is it kind of just scraping by? Well, as engineers, we need real numbers, specific parameters, so we can compare different designs and really understand how effective they are. And we've got a bunch of tools in our toolkit for this. We can look at efficiency, ripple factor, form factor, transformer utilization factor, you name it. Each one tells us a little something different about how the circuit is behaving. But for today, we're going to zero in on two of the most important ones, efficiency and ripple factor. They really give us the best first look at performance. Okay, so first up is efficiency. That's the Greek letter eta. It's really simple. It's a measure of how good the rectifier is at its job. It tells us how much of the AC power we shove in the front end actually comes out as useful DC power at the back end. And of course, you want this number to be as close to 100% as you can get. It's all about minimizing wasted power. And then there's the ripple factor. This one directly measures that bumpy output we were just looking at. It's basically a ratio of the bad stuff, that unwanted AC ripple, to the good stuff, the DC voltage we actually want. So, for that nice, smooth, clean DC output that our electronics love, we want this number to be as low as possible. Ideally, 0.
All right, that's enough theory for now, don't you think? Let's get our hands dirty and actually look at the circuits that do all this work. We're going to focus on the two main workhorses of single-phase full-wave rectification.
So first on the list is the center-tapped transformer design. The big things to notice here are 1, that special transformer. See how it has a connection, a tap, right in the middle of its secondary winding? And 2, notice that it only needs 2 diodes, D1 and D2, to pull this whole thing off.
And this is where it gets really clever. Check out the waveforms. When the input AC is in its positive half cycle, diode D1 turns on and conducts. Then, when the input flips to the negative half cycle, D2 takes over. So what the circuit is actually doing is it's flipping that negative part of the wave up, turning it into another positive pulse. We're not throwing anything away. We're using the whole wave now. It's great.
Okay, our second major design is the full-wave bridge rectifier. And you can see the key difference right away, can't you? This one uses 4 diodes, all arranged in that classic bridge shape. And it gets to use a regular, simpler transformer. No need for that special center tap. And take a look at the output. What do you know? The waveform is pretty much exactly the same as the center-tapped one. It's still doing that same magic trick of flipping the negative half cycle up. It just gets there in a different way, by using pairs of diodes that work together to steer the current in the right direction no matter which way the input is swinging.
Okay, so now we have two different circuits, and they both give us basically the same output. This happens all the time in engineering. You've got options, so which one do you pick for your design? Well, this is where you have to start thinking about the trade-offs.
And this is the classic engineering question, right? Center tapped or bridge? Which one is better? By now, you all know what the answer is going to be. It depends. There's almost never a single best answer for everything. There's only the best choice for the specific job you're trying to do.
And this table breaks down those trade-offs for us perfectly. Look at the center tap design. Its big advantage? It's simple, only needs 2 diodes. But the disadvantage is that special transformer. It's expensive and really limits you to low-power stuff. We're talking under 100 watts. Now the bridge rectifier, that's the heavy hitter. It's the go-to for serious industrial applications, and it can handle power all the way up to 100 kilowatts, a huge difference.
Okay, to make this a little more real and less abstract, let's actually look at a calculation. We're going to pull the numbers from example 3.1 in the textbook for a full-wave rectifier. This will help put some concrete values to all the theory we've been talking about.
And here's the big punchline from that calculation. The math shows that even if we had a perfect and ideal full-wave rectifier, the absolute maximum theoretical efficiency you can get is about 81%. That's a hard limit. So you might be asking, where does the other 19% of the power go? Well, in an ideal circuit, it's not lost as heat. It's actually still there, trapped in that AC ripple we keep talking about.
All right, let's just wrap this up with the key things you need to remember. First, there are 2 main types of these single-phase full-wave rectifiers, center-tapped and bridge. Got it? Second, you got to know where to use them. Center-tapped for the low-power jobs, under 100 watts, and the bridge for the high-power stuff. And finally, and this is super important for what comes next, the ripple on the output has a frequency that's double the input supply frequency. So if you have 60 Hz coming in, you've got 120 Hz of ripple to deal with.
So, look, we've done a great job. We've taken AC and we've turned it into a pulsating unidirectional DC. But we're not finished, not by a long shot. We still have all that pesky ripple to deal with. And that, of course, leads us to the next logical step in designing a power supply, which will be our topic for next time. How do we build filters to get rid of that ripple and give us the smooth, steady DC our devices are crying out for? Think about it.